Hi friends, today we will discuss about the linear harmonic oscillator by Schrödinger method. Further, first of all, we will discuss about the wave equation. Then we will discuss about the energy eigenvalue and energy eigenfunction. Okay, so to solve the linear harmonic oscillator, so first we introduce the potential energy. Here the potential energy V equals to 1 by 2 kx square. Here k is nothing but force constant. Okay, so x is a coordinate. X is coordinate. Therefore, the completely different from system. We consider that. So the wave equation is V equal the wave equation. Here we take time independent Schrödinger equation. The time independent Schrödinger wave equation is d square psi by dx square by dx d square psi by dx square plus 2m by h cut square into e minus 1 by 2 m omega square x square psi equals to 0. This is a Schrödinger time independent wave equation. So here in our convenient way we consider y equals to m omega by h cut whole power 1 by 2 into x and lambda equals to 2e by h cut omega. Okay, so y equals to m omega h cut whole power 1 by 2x and lambda equals to 2e by h cut omega. These two are new parameters y and lambda. On substituting new parameters lambda, y, the equation, the Schrödinger time independent wave equation becomes d square psi by dy square plus lambda minus y square psi equals to 0. On substituting lambda y in the place of those values we substituting lambda and y. Okay. On solving this, in this the solution of the above equation, that is in the form of asymptotic solution. So we take it as d square psi by dy square minus y square psi. Here lambda. So here y tends to infinity. So when y is very large, here lambda minus y square will become y square. So this equation becomes d square psi by dy square minus y square psi equals to 0. Okay. So this solution, its asymptotic solution are, that is in the form of exponential. So psi of x equals to this one, psi of x equals to e power plus or minus y square by 2. This is asymptotic solution. And differentiation with respect to x, twice differentiation, you will get d square psi by dy square. Okay, on substituting d square psi by dy square and psi value in this equation, you will get d square psi by dy square equals to y square plus 1 e power plus or minus y square by 2 nearly equals to y square psi. So this solution becomes psi equals to e power minus y square by 2 h of y. So this h of y is a function. This is called as harmonic function. So in the form of series solution, you will write in the place of psi, you will get in the form of harmonic function d square h of y by dy square minus 2y dh by dy plus lambda minus 1 h equals to 0. This equation is called as a harmonic equation. So then we shall look for h of y. A series solution is in the form of summation n equals to 0 to infinity an y power n. This is the series solution of h of y. So on simplifying this, that means that is in the form of d square by dy square Then on substituting this equation, the above, you will get summation of k equals to 0 to infinity, k plus 1 into k plus 2, a k plus 2 minus 2k plus 1 minus lambda into a k whole of y power k equals to 0. On substituting this, you will get this one. Okay. The validity of this equation, the coefficient of each power y must vanish separately. Coefficient of y power k when equated to 0 gives the recurrence relation. So this is a recurrence relation. A k plus 2 equals to 2k plus 1 minus lambda by k plus 1 into k plus 2 a k. This formula allows the calculation for all even coefficients in terms of a0 and the odd coefficients in terms of a1. So this is h0 of y equals to y into a1 plus a3 y square plus ay y power 4. Okay. For even, you will get a0 plus a2 y square plus a4 y power 4. So on. This is even solution. This is odd solution. So this is the Hermite solutions. Then you will start the energy eigenvalues. When k tends to 0, this k tends to 0, so then this equation becomes a k plus 2 by a k equals to 2 by k. Consider Taylor expansion of e power y square, exponential y square. The Taylor solution is summation, okay, 0.2 comma 4 1 by k by 2 factorial y power k. The ratio of coefficients of the successive terms, that is a k plus 2 by a k equals to k by 2 factorial by k by 2 plus 1 factorial, then that is nearly equals to 2 by k. So if k is large, therefore the large values of k, psi becomes psi equals to exponential of minus y square by 2 into h of y, tends to behaves like a exponential of y square by 2. This psi becomes exponential of y square by 2. If the series is even and y exponential of y square by 2, if the series is odd, this one, if the series is even, then you will get exponential y square by 2. If the series is odd, then you will get psi equals to y into exponential of y square by 2. Okay. So next, in the polynomial solution, you will get 2n plus 1 minus 2e by h cut omega equals to 0. Then on solving this, you will get the energy eigenvalue, that is E equals to n plus half h cut omega, where n equals to 0, 1, 2, 3, so on. Okay. So finally, the energy value of an oscillator based on quantum theory is En equals to n h cut omega. Okay. If n equals to 0, you will get E0 equals to 1 by 2 h cut omega. If n equals to 1, E1 equals to 3 by 2 h cut omega. If n equals to 2, then you will get 5 by 2 h cut omega. So on. The energy levels are like this. So then you will find out the eigen functions. When lambda equals to 2n plus 1, the equation reduces to, Hermite equation reduces to t square hn of y by dx square minus 2y d hn of y by dy plus 2n hn of y equals to 0. Then this is Hermite equation polynomial equation of degree n. The energy eigenfunction can be expressed as psi n of y equals to n, capital N n, h n of y exponential of minus y square by 2. Here y square is equals to m omega by h cut x square. Okay, so the first four polynomials are Hermite polynomials are h0 of y equals to 1. This is first Hermite polynomial. And next h1 of y equals to 2y, h2 of y equals to 4y square minus 2, h3 of y equals to 8y square y cube minus 12y. Then the normalization condition, that is normalization condition means integral mod of psi n of y square equals to 1. On substituting mod of psi n of y whole square is this one, nn hn of y exponential of minus y square by 2. Okay, so then the normalization condition becomes mod of nn whole square h cut by m omega whole power 1 by 2 integral minus infinity to infinity hn square of y exponential of minus y square dy equals to 0. This is a normalization condition, that is equals to 1 means normalization. Orthogonal condition means that is equals to 0. Okay. So then on solving you will get nn equals to m omega by h cut pi whole power 1 by 2 1 by 2 power n factorial whole power 1 by 2. On substituting nn value in the above equation, that is psi n of y, then you will get psi n of y equals to m omega h cut pi whole power 1 by 2 1 by 2 power n factorial whole power 1 by 2 into hn of y exponential of minus y square by 2. Finally, you will get, if n equals to 0, then you will get sin 0 of x equals to m omega h cut pi whole power 1 by 2 exponential of minus m omega x square by 2h cut. Okay, so these are the waveforms. If energy versus, so here on x-axis x and on y-axis energy levels v of x. So here you will get, this is the first energy level, that is n equals to 0. You will get the 0 point energy, that is half h cut omega. If n equals to 1, 3 by 2 h cut omega, second energy level. This is n equals to 2, you will get 5 by 2 h cut omega. If n equals to 0, you will get first like this waveform. If n equals to 1, you will get waveform is like this, from this to this. Okay, if n equals to 2, you will get the waveform is like this. The energy is 5 by 2 h cut omega. Okay, in the similar manner, for n equals to 3, you will get the energy form, the waveform is like this. So on comparing this one, so on y-axis the probability density, that means mod of psi of x whole square, this is probability density. On x-axis, this one, you will get the waveforms is amplifying like this. So n equals to 0, this one. On comparing this, you will get like this. If n equals to 1, then the waveform is like this. If n equals to 2, you will get 1, 2, 3. Okay, n equals to 3, you will get 1, 2, 3, 4. Like this waveforms are formed. Okay, so this is the waveforms. Okay, this ends about the energy eigenfunction and energy eigenvalue wave equation of linear harmonic oscillator. Thank you.